This section deals with 3 lessons from the book, 10.5, 10.6, and 10.7. We're dealing with tangents and secants and intersections inside and on and outside circles. So first we'll begin with some definitions. A tangent line. Do not confuse this with the trigonometric ratio tangent. A tangent line is a line that intersects a circle in just one place. A secant line, as you can see here, is a line that intersects a circle in 2 places. So very simple definitions there. Okay, we have met something like this before. We've done problems that involved inscribed polygons and circumscribed circles. We have just the exact opposite here. Circumscribed polygons on the outside, it goes around the inscribed circle. The reason we're introducing this in this lesson is because you'll notice each side of the polygon is tangent to the circle. Okay, and also on this page we have a theorem. I believe it's 10.2. It's very simple. Basically, it states that if you have a tangent line, it's going to be perpendicular to the radius of the circle, where they meet at the point of tangents. Something you might note about this, you wouldn't be surprised to know that problems that will key off this theorem will obviously use the Pythagorean theorem. Okay, so again, I promised you that we would examine what happens when we have intersections inside, on, and outside the circle. First, we're going to look at the angles. So do not think about linear measure in this case at all, just the angles and arcs. Okay, if you have an intersection on the inside, it's clear to see there's 4 angles created. I'm just examining x in this case. You'll notice that it intercepts an arc, and its a vertical angle intercepts an arc. Because these are vertical angles, they're equal, so I could just as easily have put the x right here. In any case, one of the arcs that's intercepted is typically larger than the other. It is possible that they're exactly the same. But in any case, the x here in the middle is the average of those. So that is to say, oops, there should be a plus. That is to say that x is equal to 1/2 the measure of the big arc plus the measure of the small arc. You need to commit this to memory. Okay, a very simple case here is if the intersection takes place on the circle. There are 2 angles created. I'm just going to look at the acute one. We could have just as easily looked at this one. And it is going to be, the measure of this angle is half the arc that it intercepts. So in this case, x is just equal to half the arc. Angle is half the arc. And then finally, outside. Now there's 1, 2, 3 different ways this could happen. I could have 2 tangent lines intersecting, or a tangent line and a secant line, or 2 secant lines intersecting. In all 3 situations, the measure of the angle is 1/2 the big arc minus the small arc. Okay, I just want to point out a couple things. If you have 2 tangent lines, the big arc and the small arc are the entire circle. So the relationship between them is that they add up to 360. If you have a tangent line and a secant line, you're only looking at part of the circle. And then finally, that's true also of 2 secant lines, just examining part of the circle. Okay, and also we can say something about segment lengths. You'll notice that I'm not examining the case where the lines intersect on the circle because one of those would be a tangent and it would have no length. To show you what I mean, this line right here doesn't stop. So nothing exciting there, nothing interesting. Okay, but if we do have 2 lines that intersect on the inside, you'll see that I broke each segment into 2 parts based on where they intersect, and it's quite interesting. This part times this part equals this part times this part. So AB equals CD. And what I tell my students to remember is that if the intersection is on the inside, it's part times part equals part times part. Okay, if it happens on the outside, so again, 2 tangents, a tangent and a secant, or a secant and a secant, what you want to remember is exterior times hole equals exterior times hole. It's very simple in the case of tangents. The exterior part for the blue segment is A. The whole thing is also A, so A squared equals C times C. And if you just take the square root of both sides, A is C. I call this the ice cream cone theorem because it looks like an ice cream cone sideways, and the 2 segments are congruent. Okay, what about if I have a tangent and a secant? Okay, again, just like up here, in this case, the exterior and the whole are both C. All right, now we're finally going to see why we say exterior times whole. The exterior part of this secant segment is A. So I'm going to say A times the whole thing. Well, that's A plus B. So A times A plus B. And then if they're both secants, exterior is A times the whole thing is A plus B equals the exterior, which is C, times the whole thing, which is C plus D. All right, let's do some work. Okay, this says TE is tangent to the circle at point T. Find Y. Well, if it's tangent, then I know it's perpendicular. That was the theorem from the very first page. If it's perpendicular, I've got a right triangle, 20, 16, and call this X. Because it's a right triangle, I use the Pythagorean theorem. There's actually a Pythagorean triple. I'll leave it to you to figure it out yourselves if you don't trust me. X is equal to 12. Well, if this side is 12 and Y is clearly a diameter, it's a diameter, it's going to be twice that. So Y equals 24. Okay, determine whether BC is tangent to circle A. Well, if this were tangent, then this would be a right triangle. So I need to see if the Pythagorean theorem works. They didn't tell me all the sides, though. This part's 7. How long is this part? Well, it's a radius, so it's going to be 7 like this other one. We need to test to see, is 7 squared, that's AB, the short leg, plus 9 squared, that's the long leg, is that equal to the hypotenuse squared? We're going to test. 49 plus 81 is 130, I believe, something like that. And 14 squared, let me check that again. Yeah, it's close enough. And 14 squared is 196. Clearly, these are not equal, so no, it's not tangent. All right, we'll try this one as well. The part that I'm missing is the 10 here. And again, if this were a tangent segment, then that would be perpendicular. Let's see if it should be perpendicular. Is 10 squared plus 24 squared equal to 26 squared? That's our question. Do a little math. I believe it's 676. 676 is equal to 676. That's correct. So yes, they're equal, and yes, we have a right triangle. I'm not positive if that's 676, but I'm pretty sure they're equal. Okay, now we're going to use what I call the ice cream cone theorem. If you forget about this big circle here, you just look at the small ice cream cone. If this is 10, then this has to be 10. So y is equal to 10. If y is equal to 10, this segment is 5. If that segment's 5, then the whole top, and now I'm looking at the big ice cream cone, the whole top segment is 15, so that means the whole bottom segment has to be 15. This part is 10, so this part is 5. Clearly, x is equal to 1. Okay, again, ice cream cone theorem. Now, this is, you can imagine one ball of ice cream and 3 ice cream cones, 2 rather ridiculous looking ice cream cones. Okay, if UI is 16, so is UF. If FH is 18, so is HM. And then they tell us NC, that's this guy, is UF plus 29. Well, if UF is 16, then NC is 45. And if NC is 45, so is IC. They said find the perimeter of the triangle. Just add up 45 plus 16 plus 16 plus 18 plus 18 plus 45. I don't even know what that is, but just add them up. Okay, and now we get to an intersection. We're talking angles. We want to know the measure of angle 3, the measure of angle 4. Well, 4 should be half this one plus this one. We don't know those arcs, so we're going to try to do 3 first. The measure of angle 3 is going to be 1/2 the measure of the big arc that it intercepts, or its neighbor intercepts 88, plus the small arc, well, it intercepts 76. 88 plus 76 is 164, and half of that is 82. So if angle 3 is 82 degrees, the easiest way to find angle 4 is to recognize that 3 and 4 are a linear pair, and therefore they're supplementary. 180 minus 82 is 98 degrees. That's what angle 4 measures. Okay, this is another angle question, and we're asked to find the measure of angle RPS. We like using x for that variable, And you should recognize that the intersection takes place on the circle. In the previous one, it took place inside the circle. So if it's on the circle, then the measure of the angle, which in our case is x, is going to be 1/2 the measure of the arc that it intercepts. The arc that it intercepts is PS. So all we've got to do is figure out the measure of that arc. Okay, well, if PT is 114 degrees and TS is 136, that means this major arc is 250 degrees. If it's 250 degrees, then the measure of arc PS is 360 minus 250, which is 110 degrees. So x is 1/2 of 110 degrees, which is 55. Okay, again, we're talking angles, and we have an intersection outside the circle. So before anything else, you need to think that the measure of the angle is 1/2 big minus small. Okay, the measure of the angle equals 1/2 the measure of the big arc. Well, this is the big arc out here, 141, minus the measure of the small arc, 17. 141 minus 17 is 124. Half of that is 62 degrees. Okay, again, we're talking angles. Again, the intersection's outside the circle. The measure of the angle, that's 55, right? That's the angle, is 1/2 the large, or the big arc, which is 6x, minus the small, which is 40. Okay, we have to find x. Well, I'm simply going to distribute the 1/2. Half of 6x is 3x. Half of 40 is 20. Add 20 to both sides, and divide by 3. We found x. Again, we have to find x. The intersection takes place outside, so I'm thinking the measure of the angle is 1/2 big minus small. Well, I can see that the big one is, they've called it x degrees, and I want to know what the small one is. Well, as I told you earlier, the big and the small make up the whole circle. That's 360 degrees. And so to get this guy, I have to take the whole circle, 360, and I have to subtract the other part, which is x. So this is 360 minus x degrees. So again, the measure of our angle, which is 40 degrees, is going to be 1/2 the measure of the big arc, which is x, minus the measure of the small arc, which is 360 minus x. Okay, so it's just algebra from this point. X minus, I'm going to distribute the negative. Minus 360 minus a negative x is plus x. All right, now I'm cleaning up. I'm combining my x's. I've got 2x minus 360. At this point, I'll distribute that 1/2. Half of 2x is 1x. Half of 360 is 180. Add 180 to both sides, so x equals 220. So that's to say, this is 220, the smaller angle is 140. Okay, and now we have another intersection inside, but in this case, we're not concerned with angles, but rather segment lengths. The intersection takes place on the inside. It's part times part equals part times part. Well, the two parts of this line are 9 and y. The two parts of this one are 6 and 6, which 6 times 6 is 36. Divided by 9, y equals 4. Yes, it's really that easy. You'll come to like the ones where the intersection is on the inside. In this case, the intersection is on the outside, so what I'm thinking is exterior times hole equals exterior times hole. So let's look first at segment IE. The exterior part is 8. The whole thing is 8 plus x, or x plus 8. And now the other line. The exterior, or the other segment, the exterior part is 10, and the whole thing is 10 plus 24, which is 34. Now it's just algebra. Distribute the 8. 10 times 34. Subtract 64 from both sides. That's 276. And divide by 8. That should be 34.5. Okay. Again, we have an intersection on the outside. What I'm going to think to myself is exterior times hole equals exterior times hole. We'll start with this one. The exterior part is 2. The whole thing is y plus 2. Okay, and on the other one, it's a tangent. So the exterior part is 4, and the whole thing is also 4. Okay, let's clean up. We're going to distribute on the left side. And 4 times 4 is 16. Now we just subtract 4 and divide by 2. Y equals 6. Okay, one more. Intersections on the outside, we're talking about segment lengths, and so I'm thinking exterior times whole equals exterior times whole. This one promises to be fairly difficult. The exterior part is z. The whole thing is z plus 2. So that's 2z plus 2 equals, again, exterior times whole. Well, the exterior part is z plus 4. And the whole thing, because this is a tangent segment, is also z plus 4. So it's z plus 4 times z plus 4, or z plus 4 squared. I'm going to distribute on the left side. That's going to be 2z squared plus 2z. And on the right side, I have to FOIL. It's z squared plus 4z plus 4z plus 16. You might find it helpful to write z plus 4 times z plus 4, so you can FOIL more easily. Okay, in this situation, I've got a quadratic. I want to move all the z squareds. I want to actually move everything to the left side. So I'm going to subtract z squared from both sides. And then I'm going to subtract 8z from both sides. And then I'm going to subtract 16 from both sides. Okay, to solve a quadratic in this situation, we're going to have to factor. The first terms are obviously z. I need two terms that multiply to negative 16. And so one's going to be positive, one's going to be negative, but they have to be 8 apart. I'm sorry, they have to be 6 apart. So I know that z has to be negative 2 or positive 8. And in this situation, you cannot have a linear distance that's negative. So z equals 8.